In this lesson, we are going to compare the many reinforcement learning frameworks out there and choose the best one. Here is a list of the 10 most important reinforcement learning frameworks out there. To compare them, I'm going to score these frameworks on a bunch of important metrics. The first metric is development status, and this determines whether the framework is receiving regular bug fixes and new features. If the framework is receiving both, then it is labeled active. If the framework is receiving bug fixes but not new features, then it is labeled maintenance. Now, of course, actively developed frameworks are better than frameworks in maintenance. And among the 10 frameworks in question, Ray Rllib, Acme, TF Agents, Tianshou, and Stable Baselines 3 seem to be actively developed. The rest are in maintenance. I have deliberately not listed frameworks that are no longer receiving bug fixes because they're abandoned and dead and probably does not have any future. The second metric is utility, or in other words, feature richness. If the framework is rich in features, it will be able to handle more use cases. The features that I looked at are the number and diversity of algorithms implemented, whether these algorithms can scale due to distributed implementations, the number of simulator APIs that are supported out of the box, whether it has good logging and monitoring support, and finally, whether it has good cloud support and deep learning framework support. Frameworks that had most of these features have high utility, frameworks that have some features have medium utility, and so on. The winners are Rllib, Garage, and Coach, and they seem to have all the most important features. Now, having a lot of features takes care of the most common use cases. But what happens when you have a very special use case that is not supported out of the box? In this case, it is useful to have a modular framework, which lets you override each and every modular piece to adapt to your very special use case. Therefore, modularity is the third metric that I looked at. And the good news is that most of the listed frameworks seem to have high modularity. Now, every developer knows the importance of good documentation. Therefore, the fourth metric is unsurprisingly documentation quality. If a framework had all the necessary pieces in place, meaning API and architecture docs, tutorials, and examples, I rated the documentation quality as good. If tutorials and examples were missing, then I rated it as satisfactory, and so on. Once again, the good news is that most of the frameworks are well documented, except for one of them. The final metric is the strength of the framework's community or ecosystem, and I believe that it is an important factor in determining if the framework will survive the test of time. To judge the strength of the ecosystem, I looked at whether a company, consortium, or university is backing the project, whether companies or researchers are currently using the framework, and the number of contributors on GitHub. It turned out that among the 10 frameworks, Ray Rllib, Acme, and TF Agents have very strong ecosystems, which might favor them in the long run. I applied a weighted scoring system based on these findings. I'm not going to discuss the scoring system in detail here, but I might leave a link for you in the lecture notes. The upshot is that Ray Rllib won, scoring 0.5 points ahead of the second best framework, Acme, and it seems like Ray Rllib, Acme, TF Agents, and Tianshou form the upper echelon among these 10 deep reinforcement learning framework. So it seems that at this time, Ray Rllib is the framework to learn. The framework is very active, as you can see from the high and consistent commit frequency in its GitHub repository. However, note that this commit history corresponds to the Ray project, and Rllib is only a part of the Ray project. So these commits do not directly reflect the commits happening in Rllib, but it's as close as it gets. The framework is very feature-rich. It has 32 algorithms spanning all different classes of reinforcement learning algorithms. Many algorithms have distributed implementations and multi-GPU support. It has support for major simulator APIs, including GIM. It has excellent logging and visualization facilities. Cloud providers like AWS and Azure supports Rllib. And as a machine learning engineer, I think that you might have a preference towards a certain deep learning framework. And the good news is that both TensorFlow and PyTorch can be used as a deep learning backend for Rllib, so it offers a lot of flexibility in that regard. The framework is highly modular, and it has extensive documentation, including architecture and API docs, tutorials, and examples. It has a very strong ecosystem. The Ray project got started in University of California, Berkeley, and is now the basis for the very well VC-funded startup Anyscale. It has many users and contributors, as you can see from the screenshot from its GitHub repository. In the next lesson, I'm going to show you how to install Ray Rllib on your computer.